Hello, I'm Mrs. J, and today we're going to cover part of Chapter 13, 13.1 and 2. You test for intervals where a function is increasing and decreasing. So suppose f of x has a derivative at each point in an open interval. Then if that derivative, if you plug in a value, if it's greater than 0, then it's increasing. If it's less than 0, then it's decreasing. And if it equals 0, then it's a constant. The critical numbers are where the derivative equals 0 or does not exist. So you do have to be careful. Fractions, if 0 in the denominator, those are also critical values. The critical point is actual point c and f of c. So then you plug it into the original equation to get the y value. 13.2 takes those points that you're finding and makes them relative extremes. Those are the high and low points where the function is increasing or decreasing change. So if it's increasing and then decreasing, you have a max. If it's decreasing and then increasing, you have a min. So the critical numbers are where the increasing and decreasing change. So if we look at this first graph, it's decreasing until it hits here at -1, and then it's increasing. So -1 is a critical number. Then it's increasing until it hits here at a +1, and then it goes down. So it is also a critical value. And notice that's also where the lows and highs are in the graph. So the critical numbers are the x values where you're increasing and decreasing change, or where the highs and lows are in the graph. Same thing. The point is these critical numbers and their corresponding y values. So -1, and then if we look, the y value was 0. And then 1, the y value is 4. Interval where it's increasing, well, it starts out decreasing. From -infinity to -1, it decreases. Here it increases from -1 to 1. So we said decreasing, -infinity to -1, and 1 to infinity. Max and min. When you're saying the relative max of, you put the y value at x value. So this one's a relative max. It's not the highest point because there's some over here. But it is a high point. So there's a high point of 4 at 1. I use this is by 1s on the x, and the y is by 2s. A relative min of, this is the relative min of 2 at, of 0 at -1. So make sure the first part's your y value and then your x value. Okay, let's try it without the graph. So we have this function. First thing we want to do is find the critical numbers by taking the derivative. If we take the derivative, 3 times 2/3 is 2. So it's 2x squared minus 2x minus 4. Set the derivative equal to 0 and solve. So if we set it equal to 0, 2x squared minus 2x minus 4 equals 0. You could use the quadratic formula. I'm going to divide everything by 2 and then just factor it. And so if I factor it, I have x minus 2 and x plus 1. Setting them equal to 0 gives me 2 and -1. Those are my critical values. To find the points, I'm going to graph it first so then I can just use the computer to find the points. So you want to plug this in y equals, use this window and graph it. And you should get looks something like that. We know this high and this low are at these two critical numbers. So it's at -1 and 2. Now when you're plugging this in, you want to plug the original in. Here, let me plug it in. So 2/3 x to the third minus x squared minus 4 x plus 2. And my window and there's our graph. And two critical numbers are this: to find the point, second and table, and we want 2 and -1. So 2, -4.7. I'm just going to round to the 10th. And -1, 4.3. So those are our two critical numbers. And then increasing and decreasing. Well, we have our points where increasing and decreasing change because that's our critical numbers. It is increasing until we hit -1. So from -infinity to -1, it's increasing. And then it decreases from -1 to 2. And then it increases again from 2 to infinity. These points are your max and min. Notice that this one's the high point. So -1, this gives us the high. So there's a relative max of 4.3 at 2. Whoops, I switched them. The -1 gives us the max. 4.3 at -1, and this one's the min. -4.7 at 2, because this was a low point. Let's try another one. First thing, the derivative. Quotient rule, bottom times the derivative of the top minus the top times the derivative of the bottom all over the bottom squared. Now if we simplify this, we're going to have x minus 4 minus x minus 3. Well, this will never equal 0 because if we set it equal to 0 and multiply this to the other side, we have -7 equal to 0. But your critical values are where it equals 0, but they are also where it does not exist. whoops, a little further down, where it does not exist. And this does not exist where we would have 0 in the denominator. So we have a critical number at 4, but there's no critical point because this is an asymptote. If we plug in 4, we have 0 in the denominator. Okay, so we can go ahead and graph it. X plus 3 and x minus 4. And then change the window, -3, 10, -6, 10. This line here, that's that asymptote that I was talking about at 4. That's the critical number. Depending on what calculator you have, some of the calculators do not even draw a line. The TI-84, I don't think it does. The TI-83 puts a solid line even though it should be dotted. And then the graph is like this and like this. Now notice that the derivative is a negative. This is decreasing. So it's decreasing from -infinity to 4. Here, it's still decreasing. You have to show that break, though, because it doesn't equal 4. But it's decreasing again. So it's never increasing. That's a 4. So it's always decreasing.